Hello, and welcome to our presentation of symbolic value flow static analysis for Ethereum smart contracts. I'm Yanis Maragdakis. This is joint work with several people, Neville Gregg, Sefis Laguardos, Konstantinos Triantafylou, and Ilias Tsatiris. We are all at the University of Athens or University of Malta, and we have a company called DDoB that does security analysis and audits for Ethereum smart contracts. So what is this paper about? This is a new kind of static analysis, which we call Symvalic for symbolic and value flow. And it tries to be very precise. It is a path-sensitive analysis. It's a static analysis, and it mixes values and symbolic expressions. So it does a little bit of symbolic reasoning, something like what you would find in Ethereum prover SMT solver. But it combines that with data log fixpoint engine that computes sets of values highly efficiently and joins them together to produce new inferences. Now, Symbolic analysis gets scalable precision through a mechanism that we will call dependencies, which we will describe. It's a generalization of context sensitivity. It's something to get us to be precise without sacrificing scalability. And this analysis architecture is applied to Ethereum smart contracts. Now, why Ethereum smart contracts? Well, first of all, let me just spread the message. If you care about program analysis or verification, you should be targeting smart contracts. It's an ideal domain. Correctness is crucial because smart contracts are programs that handle significant sums of money. The code is public. Even the executions, the dynamic executions are public. So you have the perfect landscape to apply all the techniques that you may know and love. You can demonstrate there's nothing to prevent you from actually running on industrial strength code and finding high value bugs. And even better, the contracts themselves are of fairly manageable size, up to 24 kilobytes in binary, and they reduce to their essential complexity. So you don't have much of accidental complexity, unreachable code, interactions with faraway program modules that may not really affect you. Things are distilled down to their essence. And at the same time, with all these nice factors at play, analyzing smart contracts is still a big challenge. There have been many tens of research papers that have had very, very low impact on actually finding high value vulnerabilities. There are actually studies that quantify that. They say something like 0.2% of the vulnerabilities that are deemed to be true positives are actually on contracts that hold money. So static analysis or generally verification techniques have not had the impact that they could have in this very high value domain. Now, the techniques that I'm going to present here have had a significant impact, not alone, but they have had a significant impact. They have resulted in 6 major security vulnerability disclosures. Just to quantify that, this is over funds worth many millions of dollars. We got 350K just in bounties. And these have been public disclosures, and you can read about them in popular articles on Medium or by us or by others. And you can find links to all of those in the paper. Now, I'm not going to claim that analysis alone did this. Human security expertise is pretty valuable for that. So the analysis gives a set of warnings, but a human has to actually inspect those warnings and find which ones are true positive. And I have to warn, there are not going to be too many of them. You're lucky if you get 1 out of 100 vulnerability warnings to be really, really valuable. Now, having said all of those things, analysis precision was really key in finding these vulnerabilities. We have gotten a pretty compact set of warnings, and that's why we've been able to inspect them and actually find true high-value vulnerabilities. So what's the problem with using verification techniques, any kind of verification techniques? I'm gonna take a pretty broad view of the landscape and use them to find security vulnerabilities, especially in the domain of Ethereum smart contracts. Well, the short summary is that nothing works for high-value vulnerabilities. Execution-based approaches, and by that I mean both symbolic or dynamic symbolic execution and model taking approaches. Like regardless of whether you're fully concrete or a little abstract, if you follow the execution flow, you are precise but fairly incomplete. You will get low coverage both of actual code but also behaviors. And the reason is the well-known state explosion problem. If you try to explore everything, then you will have too many states to actually be able to explore all of them. On the other side, static analysis approaches can be quite complete, but they have very, very low precision. Now, the way to illustrate this and the way to visualize it is that execution-based approaches are horizontal. What do I mean by that? We don't need to follow this code here. This is an example from the paper, but you can see we have several local variables or state variables, basically data on the heap or on the stack, if you want to think about it in conventional terms, and I've color-coded those. If you're doing symbolic execution or if you're doing model taking, what you're really doing is fairly horizontal, meaning that you keep the values of all of these variables closely associated in a real execution while you go through the program. So all of those are chained together. You know that the value 1030 for adjusted is related to this particular token value that you're simulating at this exact point, to this particular amount, to this particular sent to address, and this particular admin. Is it really related? Is 1030 related to this token? Maybe, maybe not. It's certainly related to amount, but in an execution-based approach, you link all of these together. And because of the combinatorics of just for this tiny program getting 5 different dimensions, you actually get state explosion. And if you've written any kind of analysis, you know how this is reflected. When we actually try to formalize an analysis, we talk about a concrete state being at least a triple of a program counter, a stack, and the stack could be something like a list of maps, and a heap, which could be a map of maps. But all of these are closely associated together. These huge data structures, they all go together. On the other hand, if you have a standard value flow static analysis, something like an information flow analysis or a points to analysis, the paradigm that you have is that of a set of values. So you have for every variable the possible values. They're just like a bin, like a big set of values for every variable. And they're not very much associated with each other, except with some mechanisms like context sensitivity, where you can break this into smaller sets, and you can hope that they capture the right associations. But the contexts themselves don't explicitly say, this value 1030 came from this value 1000 in amount. So in a static analysis, you don't get state explosion so much, but you do get imprecision. Now, the approach of dependencies in our symbolic analysis will introduce some chaining, some links between values, saying, for instance, that 1030 here is explicitly associated with amount having the value 1000 here, but without having those chains carry through the entire state. So that's one insight that this analysis architecture tries to integrate. Now, of course, by its own name, it's a symbolic value flow analysis. The big part of the analysis is that it has symbolic expressions. So for variables like x and y, we don't have just concrete values like 0 and 1. We also have entire symbolic expressions like 0 less than owner value, or something more complex. If you mask with 255 the division of owner value with a symbolic variable with 256, then you get that expression in variable y. Now, if you do this in an actual sample contract, you get something in the tens of thousands of rows. This is an actual number that we would get. We have expressions and symbolic values. That's roughly what our analysis tries. It tries tens of thousands of values for variables, combinations of variables and values, and tests whether something is reachable. Now, in practice, of course, to maintain that precision, we integrate the dependencies that I described earlier. So what do dependencies look like? The dependencies will look like X will have the value 0 if Y has the value 0 and Z has the value 1, and the caller is owner. And typical numbers for actual contracts are in the millions or tens of millions. So here we have, for one contract, we have 11 million rows of this table. The dependencies are of the two different kinds. There are local dependencies that are only valid inside the function, and there are global dependencies, for lack of a better name. We actually try to associate them with transactions, like who is the external caller, but also what are the public entry point arguments when the contract started executing. Again, all of these are meant as a mechanism to ensure precision, to ensure that those values are not just completely independent. We do record that X is 0 only when Y is 0. Well, or not only, but under the condition that Y is 0. There could be other conditions, but under that condition, we know that X can be 0. So we get a pretty precise analysis without sacrificing scalability completely. The overall analysis approach is one that joins together a traditional fixed point computation. So we have data log-based analysis rules. And then we have a symbolic solver, simple theorem prover. It is also expressed as data log rules. So primarily it does bottom-up reasoning. It tries to prove all valid propositions, all valid sentences actually, up to a bounded expression size. But then it also has logic for doing limited top-down reasoning, to solve equations, for instance. And these are used to suggest values to free variables. Anything that comes from an external input is a free variable, and the solver will suggest some values there. The architecture itself is one of tight integration between the fixed point logic and the symbolic reasoning, and you can see the API that gives you an idea. The fixed point logic just says, here are the expressions that I've seen, here are the free variables, and now simplify them, normalize them. Also, I can make equality requests and inequality requests and see if you can solve those and suggest values for me to try. And getting a 3-address IR as input and processing it in this way, we produce a set of values or warnings. Now, to give you an idea of the experiments, and you can read a lot more about it in the paper, we have developed a test suite. It's evolving an existing open source test suite for smart contracts called SmartBugs. We actually normalize this and we add also some high value contracts. So we think it's a great suite for future use. And we compare it to state-of-the-art industrial tools, Mithril and Manticore. And just a brief idea of the systematic results that we get something like very good recall. So we actually find 74% of the vulnerabilities in this test suite, as opposed to, say, 25% for Manticore. Manticore is a symbolic execution tool, so it has 100% precision, but at the same time, it times out for 50% of the contracts, and it only warns about half of those. Mithril, which is a combination, it's a hybrid of static analysis and some symbolic execution, gets lower recall, lower precision than ours, and lower scalability, and also the running times are much higher than the running times of our analysis. So this is a systematic evaluation, tries to show what decisions have been made to exactly capture this precision without sacrificing scalability. So to conclude, I presented an analysis that combines symbolic reasoning and value flow reasoning. We think this is a very promising direction. There's the mechanism of dependencies that can help scalability without sacrificing precision. This is an answer of sorts in a specific setting. It is an answer to the state explosion problem. And overall, I want to encourage you to work in the domain of smart contracts. It is a challenge. Lots of people are paying attention to program correctness in smart contracts. This is a very high value domain, and it gives you all the opportunities to succeed because you have everything you need to do high quality analysis in this domain. So thank you very much.